Welcome to this problem-solving session. Today, we'll be tackling LeetCode problem number 1028, recover a tree from Preorder Traversal. In this problem, we'll explore how to reconstruct a binary tree structure from a given Preorder Traversal string. Let's dive in and break it down step by step. In this problem, we are tasked with reconstructing a binary tree from its Preorder Traversal, which is given as a string. The string follows a specific structure. First, each node value is represented by a sequence of digits, with no separators, so numbers like 123 are treated as a single node value. Second, the depth of each node is indicated by a number of dashes before the node value. For example, if there is one dash before a value, that node is at depth 1, meaning it's a child of the root. 2 dashes indicate depth 2, making it a grandchild of the root, and so on. Lastly, the binary tree follows the preorder traversal order, which means we visit the root, then the left subtree, and finally the right subtree. Our goal is to recover the tree structure from this string and return its root node. The output of the problem is the root node of the reconstructed binary tree. To implement this, we will write a function called recover from preorder, which will take the input string traversal and return the root node. The function signature is provided, and it uses a class treeNode to represent each node of the binary tree. The treeNode class has 3 attributes: val, which stores the value of the node, and left and right, which refer to the left and right children of the node, respectively. Let's consider an example to better understand the input and output. Suppose the input string is 1 2 3 4 5 6 7. The output for this input string is a binary tree represented as follows. The root node has a value of 1, with 2 children, 2 and 5. Node 2, the left child of the root, has 2 children of its own, 3 on the left and 4 on the right. Similarly, node 5, the right child of the root, has 2 children, 6 on the left and 7 on the right. This tree structure is derived from the input string by interpreting the dashes as depth indicators. For example, the root node, 1, has no dashes before it, so it is at depth 0. The next value, 2, has 1 dash, placing it at depth 1 as the left child of the root. Continuing in this way, we construct the entire tree, ensuring that nodes at the same depth are placed appropriately as siblings. Now consider another example where the input string is 1-4013499088. Here, the output binary tree has a root node with a value of 1, and it has a left child with a value of 401. Node 401 itself has 2 children, 349 on the left and 88 on the right. Additionally, node 349 has a single child, 90, which is its left child. This tree structure is also derived using the same approach. For instance, the value 1 has no dashes, so it is the root. The value 401 has 1 dash before it, indicating it is the left child of the root. Similarly, 349 has 2 dashes, placing it as a child of 401, and so on. To complete the explanation of this example, we observe that the value 90 has 3 dashes before it, which places it at depth 3 as the left child of 349. The value 88, with 2 dashes, is placed as the right child of 401. By following the preorder traversal rules and interpreting the dashes correctly, we can reconstruct the entire tree. The constraints of the problem specify that the input string will always represent a valid preorder traversal, and the number of nodes in the tree can be as large as 10,000. Node values are guaranteed to be in the range from 1 to 1 billion, ensuring that the input string can represent a wide range of binary tree structures. Additionally, there are several edge cases to consider. For instance, if the input string represents a single node tree, such as 1, the output will simply be a tree with 1 root node. Another case involves a deep tree where each node has only a left child, like 1-2-3-4-5, which creates a linear tree structure. Conversely, if the tree has many siblings at the same depth, such as 1 2 3 4 5 6 7, the output will be a wide tree with the root node having multiple children but no deeper levels. Finally, the solution must handle extremely large inputs efficiently, ensuring that trees with up to 10,000 nodes can be processed within time and memory constraints. To tackle the problem of recovering a binary tree from its preorder traversal string, we explored several approaches. The first was a brute force method that involved manually handling the depth of nodes. In this approach, we parse the input string character by character, extracting node values and determining their depths by counting dashes. A stack was used to maintain the current path of nodes, and we manually associated child nodes with their parents based on their depths. However, this method proved to be inefficient, as the time complexity could reach n squared in the worst case. This inefficiency arose from the need to frequently backtrack or traverse the stack to insert nodes in the correct positions. Additionally, managing indices and updating the stack manually made the implementation more error-prone and harder to maintain, which led us to explore better alternatives. Next, we considered an optimized approach that utilized depth-first construction with a stack. This method involved a single pass over the input string to extract node values and depths. A stack was used to represent nodes at their respective depths, allowing us to dynamically manage the tree structure. When encountering a new node, we would adjust the stack by popping elements until the top of the stack matched the parent depth. The new node was then attached as a child of the top node and pushed onto the stack. This approach was highly efficient, with a linear time complexity of n, as each node was processed exactly once. The space complexity was h, where h represented the height of the tree, as the stack size corresponded to the current depth of the tree. This method proved to be both intuitive and efficient, seamlessly integrating parsing and tree construction without requiring backtracking. We also evaluated a recursive parsing approach. In this method, a recursive function was used to process the input string. For each recursive call, the function extracted the current node's value and determined its children by counting dashes and parsing the corresponding substrings for the left and right subtrees. While this approach offered a logical structure, it had several drawbacks. Although the time complexity remained n, managing substrings introduced additional overhead. The space complexity was also h, due to the recursion stack, which made it less efficient for deep trees. Furthermore, repeatedly parsing substrings added unnecessary computational overhead, making this method less optimal for large or complex inputs. Ultimately, the recursive solution lacked the simplicity and efficiency of our chosen strategy. The key insight that guided our chosen strategy was recognizing the relationship between preorder traversal and the depth of nodes. Specifically, the number of dashes in the input string uniquely identified the parent-child relationship, and leveraging a stack allowed us to dynamically adjust the tree structure. This eliminated the need for backtracking or rescanning the string. Comparing the approaches, manual depth handling was unnecessarily complex and prone to errors, while the stack-based method offered a cleaner and more efficient alternative. Similarly, recursive parsing, though logically straightforward, suffered from space inefficiencies and potential stack overflow for deep trees. The stack-based approach struck the ideal balance between performance, simplicity, and maintainability, making it the most robust solution for this problem. To solve the problem of recovering a binary tree from its preorder traversal string, we need to carefully interpret the input format. The given string represents node values separated by dashes, where the number of dashes indicates the depth of a node in the tree. Our goal is to reconstruct the tree based on this encoding. The first step involves parsing the input string. As we traverse the string, we count consecutive dashes to determine the depth of each node. Simultaneously, we extract the digits that form the node's value. To achieve this, we maintain two variables, depth, to track the number of dashes, and value, to accumulate the digits. Using a loop, we process each character. Dashes increment the depth counter, while digits are added to the value. Whenever we detect a transition, like moving from dashes to digits or to a new set of dashes, we process the current depth and value as a complete node, resetting these variables for the next node. Finally, when the end of the string is reached, we ensure the last node is processed correctly. This parsing step provides us with all the necessary information to construct the tree, the depth and value of each node. Once we have parsed the input string into nodes with their respective depths, the next step is to construct the tree. For this, we use a stack, which helps keep track of the nodes at each depth level. Starting with an empty stack, we process each parsed node one by one. For each node, we create a new tree node using its value. If the stack size exceeds the current node's depth, we pop nodes from the stack until the top of the stack aligns with the parent depth of the new node. This ensures that the stack always reflects the correct parent-child relationship. After adjusting the stack, we attach the new node to the appropriate parent. If the parent node found at the top of the stack does not have a left child, the new node becomes its left child. Otherwise, it is assigned as the right child. Finally, we push the newly created node onto the stack. Once all nodes are processed, the root of the tree will be the first node pushed onto the stack, which remains at the bottom. This step efficiently reconstructs the tree while maintaining the parent-child relationships dictated by the preorder traversal string. The algorithm relies on several important insights to work effectively. First, the preorder traversal structure guarantees that a parent node is processed before its children, which simplifies the tree construction. Second, the depth of a node is encoded as the number of dashes in the input string, allowing us to determine parent-child relationships directly. Third, the stack serves as a dynamic tool for managing the current path through the tree. It helps us efficiently backtrack to the correct parent node whenever a new child node is encountered. In terms of data structures, the stack plays a central role. It dynamically maintains the nodes at various depth levels. Key operations include pushing a new node onto the stack when it is created and popping nodes to backtrack when necessary. Additionally, temporary variables like depth and value are used during string parsing to extract node information. The algorithm is efficient, with a time complexity of O(n), since parsing the string and constructing the tree each require a single pass through the input. The space complexity is O(h), where h is the maximum depth of the tree, because the stack only stores nodes along the current path. The stack's space usage is proportional to the maximum depth of the tree, which ensures the algorithm is efficient even for deep or unbalanced trees. Now, let's consider some edge cases to ensure the algorithm handles all scenarios correctly. For a single node tree, where the input string contains only one node, the algorithm creates a tree with a single root node, as expected. For an unbalanced tree, where nodes are skewed to one side, the stack still maintains the proper parent-child relationships without any additional adjustments. For invalid input, such as a malformed string with missing dashes or values, the algorithm can include additional error handling to validate the input before proceeding. To illustrate the algorithm, let's walk through an example. Consider the input string 1 2 3 4 5 6 7. The parsing step extracts nodes along with their depths: 1, depth 0, 2, depth 1, 3, depth 2, 4, depth 2, 5, depth 1, 6, depth 2, and 7, depth 2. With the parsed nodes ready, we proceed to construct the tree. Starting with the root node, we create node 1. Next, node 2 is added as the left child of node 1. Moving deeper, node 3 is attached as the left child of node 2, followed by node 4 as the right child of node 2. Returning to depth 1, node 5 becomes the right child of node 1. Then, at depth 2, node 6 is added as the left child of node 5, and node 7 is attached as the right child of node 5. The final tree structure looks like this. Node 1 is the root, with nodes 2 and 5 as its children. Node 2 has nodes 3 and 4 as its children, while node 5 has nodes 6 and 7 as its children. This completes the reconstruction of the tree. The algorithm efficiently handles the preorder traversal string to produce the correct binary tree structure, demonstrating the power of stack-based construction and depth encoding. Here, we start by defining a tree node class, which represents each node in our binary tree. It has an initializer that takes a value and sets up placeholders for its left and right children. Next, we define the solution class and its method recoverFromPreorder, which will reconstruct the tree from the given traversal string. We initialize a stack to keep track of nodes at various depths as we parse the string, and a pointer I to iterate through the traversal string. Inside the while loop, we first calculate the depth of the current node by counting consecutive dashes. Each dash corresponds to one level deeper in the tree. Once we know the depth, we extract the value of the node by parsing the digits from the traversal string. This is done by marking the starting position of the value and iterating through until we encounter a non-digit character. The extracted value is then converted to an integer, and we use it to create a new tree node instance. Now we adjust the stack to reflect the current depth. If the stack has more nodes than the current depth, we pop nodes from the stack to backtrack until the stack matches the current depth. This ensures the top of the stack always corresponds to the parent node for the current depth. If the stack is not empty, it means the current node has a parent. We check if the parent's left child is empty. If it is, we assign the current node as the left child. Otherwise, we assign it as the right child. Finally, we push the current node onto the stack to track it as we continue building the tree. Once the traversal string is fully processed, the root of the tree will be the first element in the stack, which we then return as the result. Here, we start by defining the treeNode class, which includes fields for the node's value, its left child, and its right child. This is the standard structure for a binary tree node. Next, we move into the main solution class where we implement the recover from preorder method. This method takes the preorder traversal string as input and reconstructs the binary tree. A stack is initialized using a deque to help manage nodes at various depths during the traversal. We also initialize a pointer, I, to iterate through the string. In the while loop, we compute the depth of the current node by counting consecutive dashes in the string. Every time a dash is encountered, we increase the depth counter and move the pointer forward. Once the depth is calculated, the next step is to extract the value of the node. We record the starting index of numeric characters and keep advancing the pointer until we reach a character that is not a digit. The substring corresponding to these digits is then parsed into an integer, which represents the value of the current node. A new tree node is created using this value. To ensure the stack aligns with the depth of the current node, elements are popped from the stack until its size matches the depth. This adjustment allows us to access the correct parent node for the current depth. If a parent exists, we check whether its left child is null. If it is, we assign the current node as the left child, otherwise, it becomes the right child. Finally, the current node is pushed onto the stack, marking it as the most recent node at its depth. Once all characters in the traversal string are processed, the root of the tree can be retrieved as the earliest node added to the stack, which remains at the bottom. The method then returns this root node, completing the reconstruction of the binary tree. To begin reconstructing the tree, we start by initializing an empty stack and setting our index to 0. The first node value, 1, has no preceding dashes, which indicates its depth is 0. We parse the digits to extract the value 1 and create a tree node with this value. Since the stack is empty, this node becomes the root of the tree. We then push tree node 1 onto the stack. Next, we encounter the node value 2, which is preceded by 1 dash, indicating a depth of 1. After parsing the digits, we find the value is 2. We create tree node 2 and attach it to the left of tree node 1, as it is the next child at this depth. We then push tree node 2 onto the stack to keep track of our current position in the tree. The next node value, 3, is preceded by 2 dashes, suggesting a depth of 2. Once we parse the digits, we determine the value is 3. We create tree node 3 and attach it as the left child of tree node 2, as it corresponds to the next level in the tree. Tree node 3 is then pushed onto the stack. For the node value 4, we again encounter 2 dashes, so the depth remains 2. After parsing the digits, the value is 4. We create tree node 4 and, because we need to adjust the stack to maintain the correct depth, we pop tree node 3 from the stack. This allows us to attach tree node 4 as the right child of tree node 2. The stack is then updated to include tree node 4. Moving on, the node value 5 is preceded by 1 dash, indicating a depth of 1. Parsing the digits yields the value 5, and we prepare to process this node. To place tree node 5 in the correct position, we first pop nodes from the stack until the depth aligns with 1, which results in attaching tree node 5 as the right child of tree node 1. The stack is updated with tree node 5 as the most recent entry. For the node value 6, the 2 preceding dashes denote a depth of 2. Parsing reveals the value 6, and we create tree node 6. This node is then attached as the left child of tree node 5. The stack is updated to include tree node 6. Next, the node value 7 also has a depth of 2. Parsing the digits gives the value 7, and we create tree node 7. To adjust the stack, we pop tree node 6, which allows us to attach tree node 7 as the right child of tree node 5. The final stack contains tree node 1, tree node 5, and tree node 7, and the resulting tree structure is a balanced binary tree with the root node 1. In our second example, we process the input string 1-234-5. As before, we start by parsing the value 1, which becomes the root node tree node 1. The stack is initialized with tree node 1. The next value, 2, is preceded by 1 dash, giving it a depth of 1. After parsing, tree node 2 is created and attached as the left child of tree node 1. The stack is updated to include tree node 2. The value 3 follows, with 2 dashes indicating a depth of 2. Parsing yields tree node 3, which we attach as the left child of tree node 2. The stack now holds tree node 1, tree node 2, and tree node 3. For the value 4, the 3 preceding dashes denote a depth of 3. Parsing gives the value 4, and we prepare to place this node in the tree. Tree node 4 is created and attached as the left child of tree node 3, since it corresponds to the next level in the tree. The stack is updated to include tree node 4. The final value in this example, 5, is preceded by 1 dash, indicating a depth of 1. Parsing reveals the value 5. To properly position tree node 5, we pop nodes from the stack until the depth aligns with 1, leaving only tree node 1 in the stack. Tree node 5 is then attached as the right child of tree node 1, and the stack is updated to include tree node 5. The resulting tree structure features a root node 1, with a left subtree extending down to tree node 4, and a right child tree node 5. In the third example, the input 1-4013499088-88 requires parsing values and depths in a similar manner. The algorithm adjusts the stack dynamically to match the depths and ensures nodes are correctly attached as left or right children based on the traversal structure. This input results in a deeper tree with a more complex arrangement of left and right children. The final tree showcases how the algorithm adapts to varying depths and maintains the proper hierarchical structure of the nodes. To understand the time complexity of the recover from preorder function, let's break it down step by step. First, we consider the traversal of the input string. Here, the pointer I scans through the string exactly once, processing either dashes to determine the depth or digits to extract the value of a node. This sequential traversal ensures that the total work done in this step is proportional to the length of the string, giving us an O(n) complexity, where n is the length of the input string. Next, the depth calculation for each node is handled during this traversal by counting consecutive dashes. While it might seem like this adds complexity, the process is integrated into the single traversal of the string, so it doesn't contribute additional overhead beyond O(n). Finally, parsing the digits of each node's value using operations like isdigit and string slicing is a constant time operation per digit. Since each digit in the string is processed only once, this step also sums up to O(n) in total. Combining these, the cumulative time complexity so far remains linear, or O(n). Now, let's analyze the stack operations and their impact on time complexity. For each node, the stack is adjusted to reflect the current depth using the while loop while len, stack, depth. In the worst case, this loop could involve popping all nodes from the stack. However, it's important to note that each node is pushed onto the stack when it's first encountered and popped only once when its processing is complete. This means that the total work done by all stack operations across the traversal is proportional to the number of nodes, or O(n). When we combine all these components, the traversal, depth calculation, value parsing, and stack adjustments, the overall time complexity of the algorithm is O(n). Shifting our focus to space complexity, the primary contributor here is the stack used to store nodes during tree reconstruction. The stack size depends on the depth of the tree. In the best-case scenario, such as a balanced binary tree, the depth, and thus the stack size, is proportional to the logarithm of the number of nodes, or O log k. In the worst case, such as a completely skewed tree, the depth equals the total number of nodes, leading to a stack size of O(k). Since the number of nodes k is directly related to the string length n, the maximum stack size in the worst case is O(n). In addition to the stack, memory is also consumed for storing the tree nodes themselves. Each tree node requires a constant amount of memory, or O(1). With k nodes in total, the memory required for storing the tree is proportional to the number of nodes, or O(k), which simplifies to O(n), since the number of nodes corresponds to the length of the input string. Therefore, the overall space complexity of the algorithm is O(n). To put this in perspective, let's compare this approach to a naive implementation. A naive solution might involve slicing the string repeatedly to identify nodes and their depths, which would lead to multiple traversals of substrings. This results in a time complexity of O(n) squared, due to repeated operations for depth calculations and string parsing. In contrast, our approach processes the string in a single linear pass, avoiding redundant operations and achieving an optimal time complexity of O(n). This optimization is not just limited to time, it also ensures that space is used efficiently without requiring additional data structures beyond the necessary stack. When we analyze the best, average, and worst-case scenarios, we find that the time complexity remains linear in all cases. In the best case, where the tree is perfectly balanced, the stack size remains small, growing logarithmically with the number of nodes, or O log n, while the time complexity stays at O(n) due to the single traversal. In an average case, the height of the tree and the stack size may vary, but the algorithm's performance remains bounded by O(n) for both time and space. In the worst case, such as a completely skewed tree where all nodes are either left or right children, the stack size grows linearly to O(n). However, even in this scenario, the time complexity is still O(n), because each character and node is processed exactly once. Finally, mathematically, the proof for the algorithm's big O complexity lies in the fact that every character in the input string is traversed once, contributing O(n), and every node is pushed and popped from the stack exactly once, also contributing O(n). No operation exceeds this linear bound, leading to an overall time and space complexity of O(n). When working on this problem, one common mistake is misinterpreting the depth of nodes in the preorder traversal. The depth is determined by the number of dashes before a node's value, and it's easy to miscalculate if you're not carefully tracking these. To fix this, you should use a counter to track consecutive dashes and ensure the depth is consistent as you parse. Another pitfall is ignoring edge cases. For example, a single-node tree, trees with missing children at various depths, or very deep trees that can push the recursion limit. Testing your solution with both minimal and maximal inputs can help catch these edge cases. Lastly, inefficient parsing can lead to performance issues. If you're scanning the string multiple times, once for depths and again for values, you're adding unnecessary overhead. Instead, aim to extract both depth and value in a single pass for better efficiency. Another frequent error involves the incorrect use of recursion. Without proper base cases, your recursive function might end up in an infinite loop or produce an incorrect tree structure. To avoid this, make sure to define clear termination conditions, such as checking whether the input string has been fully processed or ensuring depth constraints are respected. Additionally, failing to validate the input can lead to runtime errors. While the problem might assume well-formed input, it's good practice to add pre-checks or exception handling for scenarios like invalid dash-depth relationships or malformed strings. This makes your solution more robust and better prepared for unexpected cases. This problem is deeply rooted in the hierarchical structure of binary trees. Since it's based on preorder traversal, the parent nodes will always be processed before their children. This ordering is critical and helps you construct the tree efficiently, whether you use a recursive or iterative method. For optimal parsing, leveraging a stack allows you to efficiently manage the parent-child relationships in a single pass, avoiding unnecessary overhead. While recursion is often more intuitive, using an iterative solution with a stack can be more robust, especially for very deep trees where recursion depth limits could otherwise be a concern. As always, communication is key when explaining your solution. Focus on how you're handling depths in parent-child relationships, and highlight why your approach minimizes inefficiencies. Once you understand the core concepts, it's helpful to explore related problems that share similar patterns. For instance, LeetCode 297 involves serializing and deserializing a binary tree, which is closely related to preorder traversal and reconstruction. LeetCode 105 and 889 also involve reconstructing binary trees, but from different traversal combinations like preorder and inorder or preorder and postorder. These problems reinforce the importance of understanding traversal-based tree construction. When it comes to alternative approaches, the iterative stack-based method is a strong choice. It avoids recursion depth issues, making it ideal for deep trees, though it can be slightly more complex to implement. On the other hand, recursion is simpler and intuitive, but it may not scale well for deeper trees due to stack overflow risks. Both approaches have their trade-offs, so choose based on the constraints and requirements of your specific problem. Finally, there's the option of multi-pass parsing. While this approach simplifies the logic for extracting depths and values, it increases the time complexity since the input string is processed multiple times. This can be beneficial for debugging because the extraction steps are more isolated and easier to follow. However, it's less efficient overall compared to a single-pass approach, especially for larger inputs. Weighing these trade-offs is important when deciding how to balance complexity and performance in your solution. Great job! To recap, we explored how to recover a binary tree from preorder traversal by leveraging recursive parsing and depth markers. Remember the importance of understanding traversal orders and applying recursion effectively. Thanks for joining, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!